All right, this is our extra practice worksheet. So the directions just say converge or diverge and by what test. So this first one is a p series where p is equal to 2/3. 2/3 is less than or equal to 1. So this series diverges. And it's by the p series test. So a nice quick one to start. My next one. This one is polynomial on the bottom. I can't factor it. So I want to use DCT or maybe LCT, whichever one applies. So because integral test wouldn't work. And that's anytime we have polynomial down here that doesn't factor, we should try DCT. So I want to compare 1 over n to the third minus 4n squared plus 6n. Compare that to just 1 over n to the third. And I think that this is bigger because I have n to the third minus 4n squared. There's a 6n here. So it's sort of like, if you're not quite sure on the comparison, that would be a good reason to do limit comparison test, just because you're not quite sure if DCT applies or not. I could probably like start plugging in numbers and stuff, but that's more work that I'm willing to do if I can just use LCT. So I do know that this is a convergent p series. So you need to say whether what you know is convergent or divergent and by what test. Okay, so we know that. And then because I'm not quite sure of this relationship, if this is correct or not, I'm going to do the limit comparison test. If I'm right about this, I would need limit comparison test because if the convergent series is on the bottom, then we don't know what's happening to the top. So 1 over n to the third minus 4n squared plus 6n. You're dividing by 1 over n to the third, so multiply by n to the third over 1. This limit usually comes out to 1 just because of the way that I always pick what I'm comparing to. And so because I got a number between 0 and infinity, I know that the original series acts the same way. So converges by limit comparison test. I forgot to label that there. All right, for my next one, I think I want to do a comparison test again. If not, if I did like integral test or something, well, let's see. Does this factor? I don't know. Let's try this out. 6 and 1, no. 2 and 3, no. 3 and 2, no. I don't think it factors. If it factored, I would try partial fraction. But since it doesn't, I'm just going to compare again. So let's compare what we have. 3n minus 4 over 2n squared minus 3n plus 6. Let's compare that to just 3n, so cut off the minus 4. Cut off the extra terms here over 2n squared. I know that this simplifies to 3 over 2n, but just for comparison's sake, again, this one's kind of hard when you have a mix, but I think as n approaches infinity, the minus 4 and plus 6 are pretty insignificant. But this 3n minus 3n will hold some weight, so it will matter. 2n squared compared to 2n squared minus 3n. So I think that this fraction is bigger overall. So my known, again, if I'm not sure, I could do LCT, but I'm pretty confident about that. So my known is that the integral from infinity, or from 1 to infinity of, let's simplify this, 3 over 2n is a divergent harmonic series. So I think I can get away with DCT. If I had extra time on my test or something, I would double check it with limit comparison. But I think I can go ahead and say that the series also diverges, because if the one on the bottom is diverging, then the one on the top is definitely not decreasing fast enough either. So diverges by DCT. All right, let's take a look at number 4. I have a rational expression that's a tie. So remember, I guess I haven't been saying this out loud, but we're supposed to be doing a mental nth term test to make sure the terms are approaching 0. So all of these are bottom heavy so far. So all the terms are approaching 0. Here, the terms are not approaching 0. The limit as n approaches infinity of 2n minus 1 over n plus 6. That's 2. So we're going to keep adding 2 in the long run, which will keep the sum growing. So this diverges by nth term test. And just because the limit comes out to 0 for the top 3, it doesn't mean converges by nth term test. It just means maybe converges by some other test. But you can see we got diverges for 2 of them. All right, this next one looks, again, almost like a p-series with an extra term. So let's go ahead and do our comparison. So we're going to compare, so this is either DCT or LCT. 4 over the 4th root of n cubed minus 6n. Compare that just to 4 over the 4th root of n cubed. So this is definitely, first fraction is bigger because it has a smaller denominator. And I know the series from, this says n equals 3 to infinity, of 4 over n to the 3/4. That's a divergent p-series. And so I can say, let's see, so the one on the bottom is diverging. So yeah, this is DCT. So this thing also diverges by DCT. I'm writing all of this out because these are DCT and LCT are pretty commonly on the free response. So you want to make sure that you're going through these steps just so that you're in that habit of doing that. For number 6, we can simplify this first. Let's do that. They're both powers, they're both base n, so we can subtract their exponents. So this is n to the 1/3 over n to the 1st. So if I subtract that, I get 1 over n to the 2/3 in the denominator, and that's back to number 1. So this diverges, and that's again by the p-series test. All right, number 7. This is geometric, and r is equal to negative 1/7. So the rule is that absolute value of r should be between 0 and 1. So this converges by the geometric series test. The question didn't ask what does it converge to, but we could do that pretty quickly. It's a sub 0, which is 7 times 1, so 7. So it's 7 over 1 plus, because it's minus negative, 1/7. That's 7 over 8/7, and that's 49 over 8. So not only do I know it converges, I know what it converges to if it's geometric. Next one is almost geometric, except the plus 2 is in the way, so we're back to a comparison test. So compare 1 over 2 to the n plus 2. Compare that to 1 over 2 to the n. This fraction is smaller. It's got a bigger denominator. And we know that the series from 1 to infinity of 1 over 2 to the n, or 1/2 to the n, is a convergent geometric series. So if the one on top is converging, the one on the bottom will converge too. So this series converges by DCT. All right. All right, what about this one? N cubed minus 8. Now, I was just thinking for a second, like, oh, I can factor that. But remember, that doesn't help you. You only want to factor if it's like a nice quadratic, basically. Because if you factor this, with that SOAP formula, you can't get the denominator to equal 0 for the other part. It's imaginary. Anyway, this is another comparison test. Compare 1 over n to the 3rd minus 8 to 1 over n to the 3rd. This fraction is bigger because it has a smaller denominator. It is known that the sum from 2 to infinity of 1 over n cubed is a convergent p-series. But this is on the bottom, so if it converges, it doesn't tell me anything about the function that's growing more slowly. So I need to do LCT. So the limit as n approaches infinity of my unknown over my known, or multiplied by the reciprocal of my known, again, comes out to 1. Because I got a number between 0 and infinity, I can say that this series acts the same as the P series, so it also converges by LCT. All right, little nth term test here. We need something bottom heavy if we're even going to start seeing if it converges. So the limit as n approaches infinity of 2n over 3n minus 2 is equal to 2/3, which is not 0. So this series diverges by the nth term test. This one looks telescoping, except, oh, and it is true telescoping, right? If b sub n is 1 over n plus 1, and you plug n plus 1 into that, you do get b sub n, or 1 over n plus 2. So I can skip all of the term stuff and say this will equal the limit as n approaches infinity of b1 minus bn plus 1. So that would be the limit as that approaches infinity of, if you plug 1 into b sub n, you get 1/2. And then b sub n plus 1 is the minus 1 over n plus 2. And so this is just 1/2. So this series converges, and it converges to 1/2. Converges by the telescoping series test. Now remember, if you're not comfortable recognizing whether or not it's telescoping, you can always start expanding out terms, enough terms until you realize what's going to survive and what's going to cancel. So all this means is if I really do have bn and bn plus 1, then only the first term is going to survive. Everything else is going to cancel. So this is just a shorter way to do that. All right, for this one, let's see. I can't do partial fraction because n squared plus 1 doesn't have a real number 0. And I can't do a comparison test with this. I guess maybe if I actually squared this out, I could. But I'm also noticing that this is 1 degree higher than this. So that leads me toward integral test. So let's let f of x equal x over x squared plus 1 squared. This f of x for x greater than or equal to 1 is positive, decreasing, continuous. So I can use the integral test. And I'm going to try to do it with all of the obnoxious little, see if I can fit this in here. Proper notation. I know we don't like that, but if you practice it now, then you'll probably do it correctly on a free response. All right, so now this is u sub that should be happening. So u is x squared plus 1. Du dx is 2x. Du over 2x is dx. So this is going to be du over 2x. So the x's will cancel, but I'll have a 1/2. So now it's the limit as b approaches infinity of 1/2, integral from 1 to b, of 1 over u squared du. So now we integrate that. Add 1 to this exponent, so this becomes u to the -1 over -1, or -1 over u, and u is x squared plus 1. And I'm running out of room, so okay, I'm going to skip one step of limits. I'm just going to go ahead and do the limit. So 1/2, when I plug b in, which is infinity, I'm going to get 0. And when I plug in 1, I'll get minus -1 over 2. So this comes out to 1/4. Now that's not what the series adds up to, but that's what the integral converges to. And so I can say that the series converges by integral test. It doesn't converge to 1/4. We don't know what it adds up to, but we do know that it does add up to something finite. All right. If I see a factored denominator, my first thought is partial fractions. So I'm going to try to split this up into something 1 over n and something 1 over n plus 3. And use the cover-up method. If n equals 0, then 3 over 3 becomes 1. If n equals -3, 3 over -3 is -1. So this is telescoping. It's 1 over n minus 1 over n plus 3. Now, I can tell if this is bn, this is not bn plus 1. So I can't just jump straight to the limit. Now, you could jump straight to the limit if you understand which terms are going to survive. But if you're not quite sure on that, then just start expanding out terms. So put in 1. You get 1 minus 1/4. So it's going to be everything until you get to 1/4 survives. So if you recognize that right now, then go ahead and stop and do the limit. If I plug in 2, I get 1/2 minus 1/5. If I plug in 3, I get 1/3 minus 1/6. If I plug in 4, I get 1/4 minus 1/7. And so see how see how you're going to get this 1/4 to cancel with this one. But 1 will survive. There will never be another 1/2, never another 1/3. So it's those 3 that are going to survive. Everything else is going to cancel down the line. All right, so this is equal to the limit as n approaches infinity of 1 plus 1/2 plus 1/3 minus 1 over n plus 3. All right, and that's equal to, what is this? This is 1, so this is 3 over 2 plus 1/3. Math is hard. Okay, so 9 over 6 plus 2 over 6 is 11 over 6, I think. So I know that this converges. It's not really a telescoping series test, but it's like telescoping adjacent. So if I had to pick a test, I guess I would say telescoping. But what we're kind of doing is what we first learned. We didn't like find a pattern in the sums, but we figured out what would be left if we added everything up. A problem like this would more likely be find the sum. The sum is 11 over 6. All right, I have time to finish the front of this, and then I think I'm going to have to do a second video for the back, so see how this goes. We need to figure out the series for this next one. So remember, it helps to write the term number underneath. And you know what? I could start at 0. I'm noticing like, these would line up better maybe if it was something like this. So you can start whatever series you write out, as long as it works, you can start at different n values. Because I'm noticing that all of these are 200 plus 10n, right? 200 plus 10n. And I know that this is a general harmonic, so I know this is going to diverge, but I can't just say that. I have to compare it to something. So I'm going to use a comparison test. Let's compare 1 over, separate this out. 1 over 200 plus 10n. Let's just compare that to 1 over 10n. So this first fraction is smaller. And we know the series from 0 to infinity, I guess it can't be 0, can it? I can't put in 0 into this, so let's just say this one's going to 1. I'm not sure if this is a problem, actually. If I knock this back to 1, I could have made it like 10 times n minus 1, I guess. But okay, whatever. Anyway, I'm going to go with this. This series is the harmonic series, so it's a divergent harmonic. All right, and then I need to use LCT because the one on top is diverging. So the limit as n approaches infinity of 1 over 200 plus 10n times 10n over 1. That comes out to 1, which is a number between 0 and infinity. So these two act the same. That means that this series also diverges by LCT. Remember, we knew it should diverge because it is just a general harmonic series, but for some reason we're not allowed to just cite that. All right, what is this one? So I'm going to say it's starting at 1 again. N is 1, 2, 3, 4, because it looks like this one is the sum from n equals 1 to infinity of 1 over 200 plus n squared. Okay, so I'm going to compare this to 1 over n squared. It's smaller. I know that the series from 1 to infinity of 1 over n squared is a convergent p-series. And so I can do DCT on this one. So this converges, there's not really any reason for me to label that. This converges by DCT. All right, so I'm going to stop this video here, and then I will make another one for the second half of this worksheet.